This is the Real Digital Transformation podcast series, empowering technology and business professionals to succeed with digital transformation. Now, here's your host, best-selling author and series editor of the Pearson Digital Enterprise series, Thomas Earl.
Hi, this is Thomas Earl, and welcome to another episode of the Real Digital Transformation podcast series. I have with me today Sam Bigdeli and Tara Javidi. Sam is the CEO and co-founder of KavAI, and Tara is also the co-founder and CTO of KavAI. Welcome, guys.
Thank you.
Thank you for having us.
Super. So today we're going to get into physical AI. So the theme of the talk today is the future of AI is physical AI, and there are various aspects to this that I think many will be interested in learning about. But I guess one question for both of you to address, however you'd like to right now, is where do you see the state of this? Where are we at in relation to AI and the physical world? And what progress have you seen and what shortcomings do you see?
Physical AI is the buzzword on everybody's lips. You know, everyone from Jensen Huang, Bill Gates, Mark Andreessen are talking about it. And it, to be honest, is not that far distance. And billions, as we've seen, has been poured into robotics, general foundation models for general robotic purposes, synthetic data, simulation. So there's a lot of activity in that area, and it's all remarkable research and work. I mean, it's all very Jetson, but it's coming. It's coming in on a more personal level. I can't wait for my robot assistant to be reliable enough to pass my wife's high standards.
So you kind of want a robot that actually picks up the banana peel and trash it rather than slipping on it, is the state of.
That would sound simple, but in physical AI, it's a hard problem.
Yeah, absolutely.
And so where are we at? Like the use of large language models, the use of large vision models, the incorporation of agentic AI systems that are designed to interact with external environments, where it can pick up the banana peel, but it might slip on it. But where are we at right now in terms of the overall curve of evolution of that, and where do you see things progressing? Are they progressing right now at a much more rapid pace in that space, or is there still a long way to go?
I think if you think about, and the robotics side of it, we started with robotics. There's this kind of a acting part, like being reactive to what you're learning, and then there's this thinking part, like being able to understand and perceive and predict. I think there's been a lot of work with synthetic data, trying to build models and teach robots, either through, synthetic data, user feedback, or, even showing videos and simulations to be very reactive and then know what they're doing. But still, I think on the area of robots, when they face new challenges and new scenarios, they would basically struggle, as the kind of example of a banana peel. And I think Tara can get into more depth on that.
Yeah, and so I guess maybe one way, and Thomas, you speed me up if you think this is too much pedantic, but current AI models right now, large language models are one of the best examples. They rely on digital data that they're basically spoon-fed. They make sense of the data after the data has been collected. And what we really want the next generation of AI to do well in the physical world is really to make make sense of the physical world. And in that sense, we want it to be like human beings in its intelligence. We don't think of a person to be intelligent if they just can fathom and infer on their data, but we want them to go in the physical world and collect the data that gives them further ability to infer. And that's where I think is sort of the next generation will be, building systems that can really solve this challenge in the real world. How can they be more comprehensively intelligent? And I give this one example. We all go to an airport, right? And there's just so much data, flying around. A baby crying, asking for ice cream from their mom. That's a data point that we completely ignore because we realize it's irrelevant to my getting to the gate that I'm going. But when I get to the gate and I realize there's nobody there, I immediately think of that moment where I was ignoring that little child, and I ask myself, did I miss like an announcement on the speakers that was about my gate change that I missed because of this baby's ice cream? So that's sort of where I see the future moving.
And so is it all about improving the way we train these models so that we give them as broad of exposure as possible to the environments that they'll need to operate in when they are trained? Or is it more about training them the best we can and then continually retraining them as they experience environments and learn more about the nuances of those environments?
So it's actually even more than the second. So definitely not the first, but I would argue that it's even more than the second. You want them to be curious and embodied in their curiosity. So again, going back to the airport example, you want an intelligent person to decide, okay, I missed my information from the announcement. Who is the best source of information? Oh, and a gate agent, and sort of process that physicality of where the source of the data is, and sort of walk through it and walk towards it, both figuratively and literally.
Mm-hmm.
Yeah. So you want it to be curious and embodied in the physical world, in sense.
Right. Go ahead, please.
Tara is making this sound simple, but she is as modest as she's brilliant. So I like to say this is not an easy, thing to, achieve, and no one else has done it before. I mean, there are a lot of people working on the concepts, but so the work that we have done, it's based on decades of research and foundational research in deep tech development, and we've brought on board a dream team of people working in this area of how to collect information. And in the physical world, you have so much information that is constantly changing every second. And depending on your application and response time needed to survive can be milliseconds. And you also have very little ground truth or, pre-training. And that's where your multimodality of having different type of sensors kind of play a major role. So your embodiment, as Tara mentioned, ability to move with the multimodality that you have, and all of these together as a full system, it enables you to build these hypotheses and curiously go after proving or disproving those hypotheses. So it's a complete system that enables us as human beings to really go into unknown territory and quickly learn and filter the noise pretty much.
Right. And perhaps become always aware of what is noise and what isn't. And perhaps also, evolve to a point where even the curiosity is is broadened? Like, do you foresee robots and other devices and machines with AI capabilities being able to broaden their abilities beyond what they are initially designed to do once they recognize that they can do more than what they're being, assigned to do? Or do you see it more as them fine-tuning, continually trying to do better at what they are designed to do? How far do you see the evolution going in that regard?
So it really depends on what you mean by designing them to do, right?
Mm-hmm.
So so definitely in what Sam was talking about, we want the models to be foundational and self supervised or autonomous in that sense of generating confidences around hypotheses. But at the same time, we want them to build upon the physicality of sensing and sensors that they are coming with or they are coming in contact with. So you don't want them to ignore all that information. That's the embodiment that allows humans to operate. We know when we go away from source of sound, the sound gets dimmer, right? So that's the kind of knowledge that it's being built or trained to do. And we don't necessarily need to forget that or think about like, a system that suddenly you just deals with Superman, I suddenly immediately knows what to do. That's not the direction we're thinking. We really want that knowledge to have been a part of the design of the system, to know my cameras have this property, right? And you don't want to ignore that. So in that sense, that those are things that you're designing with, and that's what they inherit. You don't want them to kind of hallucinate about, oh, now my camera can see behind the wall. Right.
In terms of hallucinations and misinterpretation of what they see or assumptions that are being made, how is that being addressed these days? Is that still a major concern?
In where we are seeing, curious systems, basically they're in a controlled hallucination because you are constantly building hypotheses and use those hypotheses to kind of predict what the sensory measurements should be. And then you go into the real world and collect information and see if your hallucination has any ground in reality. And so our systems are kind of works to reverse. We like more hallucination because we're validating that hallucination and kind of ranking, getting our prediction list saying, okay, you and I, if you're walking on the street and see like something that looks like a snake, if we don't hallucinate, we die, like we need to know all the possibilities, even if it's a rope. So in that sense, if you are envisioning or kind of hallucinating and you're validating it with information, that's actually the beginning of learning quicker than having all the data points in the world and try to be very deterministic sometimes.
Mm-hmm. Mm-hmm. And in terms of the scope of what we're discussing, is your focus on robotics specifically, or does it go beyond that?
No. This is, I think, in the beginning of the conversation, think of the world as like there's an aspect of thinking, even that applies to robotics, understanding, awareness, like this collection of multimodality information. Our world it's a wide spectrum of frequency, right? And we want to understand that world in time and space. And that can apply to robotics and enable the robot not to slip on that, banana peel. But it has other applications. We can look at anywhere you have a vast amount of time and space information, and you kind of lose, you get lost in that time series of information. You want to be kind of filtering noise through your hallucination or hypothesis that you're building based on some prior beliefs. So, as an example, we took an energy industry. This might give you some context. As you look at, let's say, a petrochemical site, it's such a complex environment, and even human beings cannot cover 300, 500 acres of land. And we're losing 300 billion a year just to unplanned shutdowns. And some of these shutdowns can be prevented, by just somebody actually seeing something. So our ability to collect all that information, build hypotheses, narrow down, this is a function in a control loop that kind of mimics human curiosity and enables the system to continuously kind of learn and improve its awareness of the environment.
Mm-hmm. Yeah. And there might be or might not be robots involved, right? In the example that Sam is talking about, you have CCTV cameras, you have some robots that can go around and precision robots that measure the thickness of the pipe, right? So it's the combination of all. But from our perspective, it's the process of orchestrating the information into digital data that then can be consumed by your foundation model. That's where we think of physical AI, and it's much broader than just robotics.
Mm-hmm. Right. Makes perfect sense. In terms of the different types of language models that you work with to address all these concerns, could you share some information about that as part of the research you're doing? Where is it going in terms of not just an LLM but the other variations?
Yeah. So basically, you in some sense, our models are foundational in the sense that they want to predict what comes next, but they're not language in specific. They are predicting the state of the world. And then there is the rub, because there is absolute lack of an absolute fidelity measure, right? So what is the state of the world? And that's where our models are very unique to our technology, to really turn the state of the world from something really big and hard to wrap your head around to something tangible that works around what fidelity is needed. And that's how that curiosity, that closed loop operation of let me hypothesize, let me collect data works. So it's sort of in certain aspects, it's similar to the language models, that it has architecturally components similar to the attention head and whatnot, but it's far more physical. It basically enables a physical attention. And in some other ways, it's quite different in its closed loop operation of taking the data, use that inference to then guide the next data point that you're collecting. That's quite unique, and it's not a part of current models and architectures that we have seen, except for the ones we are working on.
Mm-hmm. To build on what Tara says, think about a savant and a kind of a normal human being, and LLMs are kind of moving towards the savant state, and we are thinking, if we are ingesting that much information in order to operate, we won't be able to operate in the physical world. And one of the key, kind of disorders in savants are they have so much information and they can absorb so much information. They're very knowledgeable and they can answer any questions. But in order to operate in an uncertain, constantly rapidly moving information, that's why savants, get overwhelmed in big cities, and environments that just too much information. So part of us kind of being human through evolution is because we have managed to filter that noise by driving our data acquisition by something purposeful. And I think the future is one of the major kind of developments are going to be in curiosity-driven systems, and it's going to revolutionize machine learning and awareness. And consequently, it will have dramatic improvement in safety, efficiency in every major industry.
So let's then talk a bit more about what specifically your company is focusing on. If we can learn a bit more about KavAI and what you're developing and your products and services, I think that would be it would tie nicely into what we've been discussing.
Yeah. KavAI is building, as we kind of mentioned, artificial curiosity. It's not a tweak of existing models or architectures. It's something entirely new, built to allow machines to interpret and kind of interact with the world the way humans do, which is through our curiosity. In terms of use case and where we want to kind of apply it and kind of showcase what it can do, we have chosen the energy industry. Our need for energy is growing exponentially. There's some conversation around 60 gigawatts of power is needed. And that's like 60 power plants, and we're not even building one today. And some of our facilities are old, and that's where we thought, and really research, and it's a great area. You got a lot of complexity. You have a lot of sensors. You have different sensing modalities, and predicting a live energy with all the mechanical structures and mechanical assets and other structures. It's an area that you can really show what our system can do in terms of predicting and making recommendations. And that's where that's our lab, showing how these systems can prevent disasters, prevent fatalities, and optimize operations.
Super. And one last question, in terms of looking ahead to how all this will evolve over time, Tara, at what point will the robot not slip on the banana anymore? Is that a year away? Is that 5 years away? Where do you see it going?
So I think the first generation of these AI systems that are going to come along are going to depart from these classic models that are trained on data that has been spoon-fed to them. And I think the race for this next generation of AI will come from systems that really understand the physicality of data sources and really builds on an information-centric AI, really trying to turn information to data. And then this is a full-scale learning platform. We humans use our brain. That's the foundation model. That's what we have. But also we have a central nervous system, a spine, hands, eyes, ears that allow us to curiously explore the world. And that's where I think is the next generation going to happen. And this is immediate. This is something we're working on. This is not fantasy. But I think as soon as you start that progressively in time, you will see better and better capabilities being built on this core information-centric AI.
Super. Well, thank you both so much for your time today. It was very interesting and insightful. And hopefully we'll get a chance to reconnect in the future and just see where things are at then.
Thank you so much.
Thank you for having us.
Thank you for listening. Follow Thomas on LinkedIn